we talked about evolution in closed systems, which is exactly what a universal, idealized quantum computer wants to achieve. Real quantum systems, however, are not closed systems. They are open systems, which means that if you have a system of interest, for instance, your quantum processor, it actually is embedded in an environment or a thermal bath. And what happens is that your system interacts with this environment in a largely uncontrolled fashion. And since this interaction happens, the system's own evolution is no longer described as a unitary operation. It's described by a very different mathematical object. Technically speaking, it's a CPTP map, which stands for completely positive trace-preserving map. But we are not going to work with this. We just have to keep this picture in mind, that you have a system interacting with an environment which destroys the unitary nature of the evolution. So to get a sense of what is going on, let's talk about decoherence. So we introduce density matrices. So now take the density matrix of a pure state. For instance, take the density matrix of the equal superposition of the 0 and the 1 ket. And we can mix it with random noise, which is just the identity matrix divided by the number of dimensions. So this would correspond to the maximally mixed state, the classical uniform distribution. And we can control how much noise we have by tuning this parameter called visibility between 0 and 1. So with visibility 1, we have the pure state, but with lower visibility, we mix in this maximally mixed state. And the more we mix, the more the coherences vanish. And when we reach 0 visibility, we end up with the maximally mixed state. So the speed at which happens affects our quantum calculations, because we want to finish the calculation before the system completely decoheres. This is sometimes called the T2 time, and it's one of the characteristics that you look at when you study how good a quantum computer is. Another way of looking at it is as an equilibration process. So this model is actually the exact same thing what happens to a cup of coffee. So if you take a cup of coffee and you remove the lid, then you have a lot of interaction between the environment, the room where you are in, and your coffee. So it's going to cool down, and it is going to attain the temperature of the environment. So this is when it becomes in a thermal equilibrium with the environment. Once this happens, you are in a particular state, and for the quantum system, this is called the thermal state, and this is a very specific form. The energy, the configurations corresponding to certain energies follow a particular probability distribution, which is the Boltzmann distribution. So here you have this, the exponential of the energy divided by the temperature. This is the temperature, divided by the partition function, which is just a normalization factor, so that you are actually having a probability distribution. So now if you look at what it means, if you have 0 temperature, then this is just a single point, which is called the ground state. If you have some finite temperature, then this is going to look like something like this. So this is some finite temperature. And if we go to the infinite temperature limit, then this completely flattens out, which also means that this energy distribution is basically the uniform distribution. So this again corresponds to the case of a maximally mixed state.